Hi everyone, I'm the leader of the group, Tan Zijuan. Today we will be presenting our topic, which is carbon allocation. And now I will pass the presentation to Wenjun.
I'm Wenjun. In today's rapid growing urban environment, efficient car park allocation has become a problem faced by many cities. The demand for parking space usually exceeds the available supply. Therefore, this project aims to show how the concepts of discrete structures such as sets, relation, functions, and pigeonhole principles can apply to address the problem of inefficient car park allocation. We'll be using these three concepts to model car parking allocation in four distinct scenarios. I will pass the mic to Ng Wenyi.
Okay, so firstly, I'll be talking about the concepts that we've applied to our parking allocation system. So first and foremost, it would be the pigeonhole principle. So the core idea of this is that if there are more items than containers, then one container must hold more than one item. And the reason for this is because there's insufficient space for every container to hold only one unique item. So the mathematical proof has also proven that the function cannot be a one-to-one function, or it is also known as a injective, else a collision would occur. So the collision is the meaning of booking two cars into the same parking spot. And the generalized definition and mathematical proof can also state that if n objects are placed into k containers, at least one container contains n over k objects. So the answers that we've calculated using this has also utilized the ceiling function, which is the rounding up of the answers. So for instance, if we get our answer as 2.3, and using the ceiling function, we would have an answer equaling to 3 using the ceiling function. So the set theory is a mathematical method used to group collection of distinct objects that are known as sets, and it also studies the relationship between different sets. For example, set C is known as the car set, and set P is known as the parking spaces set. So there consist of three types of sets, which are known as finite, infinite, and empty set. So the finite set would be a limited number of elements. The infinite sets would consist of unlimited number of elements, and the empty set would contain no elements. So a mathematical example, as you can see here, would be the set of fruits. We can label it as F, and it will equal to apple, bananas, and mangoes, and other fruits. So the last concept I will talk about would be the function principle. So the function is a rule that maps each input from a domain to exactly one output in a codomain. For example, a car can only occupy one parking space. So in this instance, the car would be a input, which is the domain, and the parking space would be the codomain, which is the output. So these are the mathematical examples on how you can do the notation for functions. So next, we would talk about the applications of all these concepts into our parking allocation system. So in this, we've utilized three main concepts, which are pigeonhole principle, the set theory, and function. So the first application using pigeonhole would be general parking capacity. And the second thing we will be using is set theory, which we use to separate cars and parking spaces into different sets, then using the Cartesian product and function rule to determine every combination between cars and parking spaces at the same time. This ensures that only one car is occupying only one specific spot, and this can avoid problems such as double booking.
The table below shown applies the pigeonhole principle to analyze parking availability across different time intervals on campus. The principle states that if the number of cars exceeds the number of available parking slots, at least one car must be unable to park. So in this scenario, the total parking capacity is 3,750 slots. From 8 a.m. to 4 p.m., including the intervals 8 to 10, 10 to 12, 12 to 2 p.m. and 2 p.m. to 4 p.m., total parking demand stays below app capacity, ranging from 3,000 to 3,300 cars. These intervals are classified as stable periods where no parking shortage occurs. Between 4 p.m. and 6 p.m., an early congestion period appears. During this time, 1,030 and 300 reserved cars and 2,500 public cars arrive, bringing total demand to 3,080 and 800 cars. Since this exceeds capacity by 50 cars, the principle guarantees that at least 50 cars cannot find parking. So after 6 p.m., demand drops to 3,000 cars, well below capacity. This indicates that congestion is temporary and mainly concentrated in the late afternoon. So this analysis shows that the parking shortage occurs only when demand exceeds supply, which directly demonstrates the pigeonhole principle in a real-world setting.
Moreover, overflow prediction can be done by applying recurrence relation. This can be done with the formula yt equal yt minus 1 plus a minus x. This means the remaining space this hour equals to last hour space, plus cars leaving minus cars entering. So the value of yt will decrease every hour until it is less than or equal to 0. This means that the parking lot is full and cars will start cleaning outside. This is overflow. Lastly, by applying these concepts in real world, for example, pigeonhole principles allow us to alleviate the shortage of parking space without expanding the parking lot areas, but through optimization of routes. Let's say for reserved and parking slots during peak hours, some parking space can be converted into a special spot to cope with surge in demand.
Okay, thank you, Maman. So now I will conclude everything. This project demonstrates how district structure concept can be effectively applied to solve real-world problems such as car park allocation. By using set theory and function, we were able to design a clear and conflict-free assignment between cars and parking slot. The pigeonhole principle allows us to mathematically prove that parking shortage are unavoidable when demand exceeds capacity, especially during peak hours. Through time-based analysis and overflow prediction, we show how congestion can be anticipated and managed without physically expanding parking space. Overall, this project highlights that discrete structure is not only theoretical, but also a powerful tool for creating smarter, more efficient, and fair parking management system. That's all from us. Thank you so much.